Good afternoon. This is the Chemistry 122, Chapter 16 quiz review. Start with the first one. In which one of these solutions will acetic acid have the greatest percent ionization? In all of these, with C and D, you have the acetic acid in equilibrium with if you just had acetic acid, you'd have that equilibrium. But if you had added acetate anion, this is an equilibrium system. If you add sodium acetate, the equilibrium shifts back to the left to decrease the concentration of your acetate anion. Therefore, the ionization in these two situations where you have the acetate anion is greatly reduced. It's the common ion effect. Look at acetic acid and HCl. What's going to be present? If acetic acid ionizes, you produce more H+. HCl is going to ionize 100%. As the acetic acid, if it ionizes at all, it's going to produce more H+. What does a system that is an equilibrium system do? If more of a product is produced, it shifts back to the left to decrease the concentration of H+. Therefore, B, C, and D will have lower ionization than A. A, all we have is acetic acid. So we have the acetate anion and the H+ cation. So that is why the answer to number 1 is A. Number 2. Which of these mixtures forms a buffer solution when two of them are mixed together? 1 molar, 0.1 molar HCl and 0.1 and 0.1 molar sodium chloride. B, 0.15 molar nitric acid and 0.15 molar sodium nitrate. D, 0.1 molar HClO4 and 0.1 molar NaClO4. Or E, 0.15 molar HBr and 0.15 molar sodium bromide. Well, what kind of acids are HCl, HNO3? So what kind of acid is A? HCl is a strong acid. B, HNO3 is strong acid. C, HClO4 is a strong acid. E is HBr. Strong acids do not make buffers. Buffers require equilibrium processes. When the HCl dissolves and ionizes, it doesn't go back. There is no equilibrium. The arrow only goes one way. So it cannot be a strong acid to make up a buffer. So the only one of these where we have a weak acid is HF. Is the HF paired with something that has a common ion? Well, it is. HF, if that busts up, produces H+ and F-. If we introduce to that a solution of sodium fluoride, do we have the common anion? Yeah, we do, F-. So this will set up an equilibrium system. So the only mixture here that can be a buffer is answer C. Buffers are formed by combination of the weak acid and a common anion salt. Doesn't necessarily always have to be sodium, but many times it is the sodium salt. pH of the solution, that is 0.4 molar in HOCl and 0.05 molar in sodium hypochlorite. In HOCl plus H2O gives you H3O plus and OCl minus. Since we don't include water in the reaction scheme, it's not H3O plus we write, it is H plus. If we look at that reaction, the Ka for that reaction, Ka is equal to the concentration of H plus times the concentration of OCl minus divided by the concentration of HOCl at equilibrium. We know the Ka for HOCl is 3.2 times 10 to the minus 8. 3.2 times 10 to the minus 8 is equal to the concentration of H plus times the concentration of OCl minus divided by our initial concentration of HOCl. We have HCl, HOCl, and OCl. We mix them together and equilibration occurs. We have initially 0.410. Initially 0.050. Initially, we're not considering this. Initially, our H plus is 0. We mix the HOCl and the OCl together. Equilibration occurs. The equation goes from left to right. HOCl ionizes. It produces we don't care about the water. The amount of HOCl ionizes. How much? We don't know. Letting it be represented by X. Since this is a 1 to 1 to 1 mole ratio, the amount of H produced is equal to the amount of HOCl that ionized. So is the OCl. So this is minus, this is plus, and that's plus. So at equilibrium, 0.410 minus X, this is plus X. Remember, we didn't start out with 0 OCl minus, we started out with 0.05 molar. So this value is 0.05 plus X. Plug these values at equilibrium back into our expression for Ka. It's equal to the concentration of H plus, which is X, times the concentration of OCl minus at equilibrium, 0.05 plus X, divided by concentration of our HOCl at equilibrium, 0.410 minus X. Ka is equal to 3.2 times 10 to the minus 8. If we neglect, now notice, this is not necessarily X squared. This is a more complicated problem to work out. Here again, we have a weak acid. The weak acid does not ionize. Excuse me, I got to clean the screen off a little bit. Sorry. This acid, HOCl, doesn't ionize to any significant extent. So we can neglect the X term. This then simplifies to X times 0.05 divided by 0.410. So X equals the H plus concentration is equal to 3.2 times 10 to the minus 8 times 0.410 divided by 0.05. We solve this for a hydrogen ion H plus concentration. It asks for the pH. pH is equal to -1 times the log base 10 of our H plus concentration. Solve this for X. Do -1 times the log base 10 of our H plus concentration. You should come up with a value 6.58. Number 4, consider the buffer solution prepared from HOCl and NaOCl. What is the net ionic equation for the reaction when sodium hydroxide is added to this buffer? Well, if we have HOCl and water, what does the HOCl do in water? It donates the H plus and becomes OCl minus. If we bust this up, this is our ionic equation. If we do not focus on the water being present, if we add OH minus to our equilibrium, this is an acid. What does an acid do with a base? It forms water and the corresponding salt. Well, water, H and OH, H2O and OCl minus. So this is the net reaction that occurs when OH anion is reacted with the HOCl and the OCl minus buffer solution. Answer A. Number 5. For which type of titration will the pH be basic at the equivalence point? Again, we've talked about the general titration shapes and curves. That option which shows that you will have a basic pH at the point where you reach the equivalence point is the weak acid versus strong base titration. So pH 2, let's do this on the outside. 2, 4, 6, 8, 10, 12, 14. This is volume of base your equivalence point is somewhere here, just a little bit above 8, somewhere between 8 and 9. So where will you have a equivalence point that is basic? You have it with the weak acid. Again, weak acid, the pH of your starting solution starts about 3. It doesn't necessarily go all up to 12. It goes a little bit below 12. So the point at which you get the equivalence point for a weak acid strong base titration is where your pH is above 8. Number 6, 24 ml with 0.25 molar sodium hydroxide solution is titrated with 0.1 molar HCl. What is the pH of the solution after the hydrochloric acid has been added? Well, let's look at this. What kind of reaction is this? It's an acid-base reaction. What kind of acid and base are you reacting? Write it down. HCl plus NaOH. HCl, strong acid. NaOH, strong base. We write the arrow only going in one direction because this is a strong acid, this is a strong base. When they react with water or with each other, the reaction only goes one way. What's formed when a strong acid reacts with a strong base? Water and the salt. Well, since this arrow only goes one way and there is no equilibrium that goes on, after these are added and reacted with one another, whatever is left over, if we have excess HCl left over, what does HCl do? It reacts to form, if we have no NaOH left over, we've consumed it all we have is HCl left over. If it's in water, it produces H plus and Cl minus. So if we have only HCl left over because all our sodium hydroxide has been consumed, the pH of the solution is going to be determined by the concentration of your HCl. If we've added excess NaOH, all your source of H plus has been consumed. When sodium hydroxide is present in water, all you have left that determines the pH is the OH minus ion. So what we need to do is we need to figure out how many moles of HCl and how many moles of sodium hydroxide solution we have. So we have 0.024 liters of your NaOH solution. This is, let me see, 1 liter NaOH and 0.25 molar NaOH. Liters cancel, so it's 0.024 times 0.25. This is the number of moles of sodium hydroxide that we have. Let me pause this just a second. Let me get a calculator. Appreciate your patience. So we're going to take 0.024 times 0.25. 0.024, 0.25. This is equal to 0.006 moles NaOH, or just OH minus. So we have 0.006 moles of OH. We have 0.1 molar HCl. We've added 0.024 liters HCl solution. It's not 0.25 molar, it's 0.1 molar HCl. So this is 0.024, excuse me, 0.024 times 0.1. This is 0.0024 moles HCl. So we have 0.00 0.024 moles of our HCl. Well, what is larger, 0.0024 or 0.006? Well, 0.006 moles is larger. So we consume all of our HCl minus 0.0024 moles, but we don't consume all of this. We only consume 0.0024 moles. So we have excess OH minus left over. We have 0.0036 moles of OH minus left over after the reaction. So the only thing that is determining pH is our OH concentration. We've consumed all of our acid. We have 0.0036 moles of OH minus left. So we have 0.0036 moles of OH. So what? Remember, pH plus POH is equal to 14. This is 0.0036 moles of OH. But what volume is that moles of OH contained in? Well, we had 24 ml of our sodium hydroxide and 24 ml of our HCl. So we have a total of 48 mLs that contain that 0.0036 moles of OH. Molarity is moles per liter. If we're specifically looking at molarity of RH, it's the moles of the OH minus ions. So molarity is 0.0036 moles divided by 0.048 liters. I get 0.075 molar OH minus concentration. POH minus 1 times the log base 10 of our hydroxide anion concentration. POH minus 1 times the log base 10 of 0.075. So our pH is, we log of that value, times minus 1, our POH is 1.12. Stick it into our equation. pH plus 1.12 is equal to 14. pH is equal to 14 minus 1.12. pH is 12.88. So your answer here is D. Methyl red is a common indicator used in acid-base titrations. It has a Ka equal to 6.3 times 10 to the minus 6. It's unionized form. So we're talking about HIN. The unionized form of methyl red. In its unionized form, it's red, RED. In the ionized form, the IC is a yellow color. Ka for this is 6.3 times 10 to the minus 6. This is the acid strength of this indicator. If we take the log base 10 of the Ka value, we can get a log base value called pKa. This is related to, in a similar fashion, to the pH. pH is minus 1 times the log base 10 operation on your hydrogen ion concentration. Ka is a measure of how strong an ionization is it. So if we take the log base 10, multiply the log base 10 of 6.3 times 10 to the minus 6, and multiply it by minus 1. So log 6.3, 6.3, and the pKa is roughly about 5.2. This means once we get to a pH anything greater than 5.2, we're not existing in the protonated form. We're existing as the ionized form. Therefore, once we reach the pH of about 5.2, it's starting to change from red to yellow. Since we're at a pH of 7.8, we're in the yellow form. Number 8, which of the following compounds is more soluble in acidic solutions than pure neutral solutions? We are looking at here, how would each of these species dissolved in water? What would it create? This would create, if it was soluble in water, carbonate, copper iodide. Okay, so bromide, then ammonium nitrate. If we're looking at these reactions in terms of equilibrium, we add acid to any of these? Is that going to disturb the equilibrium in any way, such that we would have more of the solid dissolve into the water? Well, if we're looking at what we're adding to this mixture of ions, what are we adding? This is what we would get if we have just pure water. But what if we have an acidic solution of water? Well, let's look at the I minus, the Cl minus, the Br minus, and the NO3 minus. If we add acid to this, H plus, to the copper iodide, or to the lead chloride, or to the silver bromide, the copper is not going to react with the H plus. The lead cation is not going to react with the H plus, neither is the silver cation. The only thing that will potentially react, these are all cations. Why is a cation going to react with another cation? You've never seen that. The only thing that could react with the anions present here is H plus. Well, does H plus react with the I minus? No. Why? Because this is the salt of a strong acid. HI is a strong acid. If we form it, it goes right back and forms the I minus and the H plus. If Cl is the anion of a strong acid, it has no tendency to react as a base. So even if one Cl anion picked up a hydrogen, it would form HCl, but that would ionize right back to form the H plus, the Cl minus. Same thing for the bromine. HBr, strong acid. It has no tendency to go and form the Br minus, the HBr. Notice, ammonium nitrate. It busts up to form the ammonium cation and the nitrate anion. If the nitrate picks up H plus, it forms nitric acid. Is that a strong acid? No, it's not. So this nitrate has no tendency to react with the H plus. None of these reactions for B, C, D, and E have any tendency to react with the H plus because they're anions of the strong acid. Let's look at barium carbonate. We have barium cations and carbonate anions. When carbonate anion reacts with a strong acid in water, we get the formation of water and CO2 gas. So this is where we get that reaction where you take either baking soda or baking powder, react it with an acid, you see the formation of carbon dioxide gas, you get the bubbling. It's because the carbonate anion is being converted to H2O and CO2 gas. What happens when you have carbonate anion dissolved in water? You form H2CO3. H2CO3 is unstable. It busts up to H2O and CO2. So when we add barium carbonate to water, it busts up to some small extent to the barium cation and the carbonate anion. But when we add acid to it, the carbonate further reacts to form H2CO3 and gives you H2O and CO2. The H2O and the CO2 bubbles off. You are decreasing the concentration of Cl3. the carbonate anion. As this concentration decreases, you're changing this equilibrium. As your concentration of carbonate anion decreases, the equilibrium shifts to the right to replace the carbonate anion that is removed because it's changed to H2O and CO2. The equilibrium shifts to the right, and so more of your barium carbonate dissolves in water, in the acidic water, than any of those others, because your carbonate anion is changed into CO2 and CO2, H2O and CO2. So of these, your barium carbonate will be more soluble in acidic solutions than it is in basic solutions. Much more of this will dissolve in acidic solutions than it will in neutral pH water. Number 9. Calculate the minimum concentration of chromium plus 3 cation that must be added to 0.095 molar sodium fluoride in order to initiate a precipitation of chromium fluoride. So we write the equilibrium reaction between the cation and the anion of your chromium fluoride complex. Your plus 3 chromium cation, your 3 minus fluoride anion. Your solubility product, or the minimum concentration of your chromium and fluoride anions that you need for insolubility to result. You have as much chromium and fluoride ions in solution as you can. The KSP for this is 6.6 times 10 to the minus 11th. So when your concentration of your chromium and the concentration of your fluorine reach a value of 6.6 times 10 to the minus 11th, which is not very much, you can't get any more of the ions in solution, so this doesn't dissolve. So the KSP, the solid, is equal to the concentration of your chromium times the concentration of your fluoride cubed. So it's asking us to calculate this concentration. Let me see here. Just a second, I want to make sure I'm working this out right. Okay. Our KSP is equal to our concentration of our chromium cation. Thank you for your patience. Thank you for waiting. Times the concentration of our fluoride anion cubed. KSP is equal to 6.6 times 10 to the minus 11th. We're asked for how much chromium has to be present such that when we multiply it by the concentration of fluorine cubed for the coefficient in front here, concentration of fluoride is 0.095. We need to cube that. 0.095 cubed is 8.57 times 10 to the minus 4. X is the amount of chromium that we would have to have such that we have all the chromium cation present in solution and no more can dissolve into water. So 6.6 times 10 to the minus 11th is equal to X, our amount of chromium, times 8.57 times 10 to the minus 4. Solve for X, divide both sides by 8.57 times 10 to the minus 4. We get 7.7 times 10 to the minus 8, which is your answer C. The KSP value for lead 2 chloride is 2.4 times 10 to the minus 4. So again, write down your equation. KSP is equal to the concentration of our lead times the concentration of a chloride anion squared. Thank you for being patient. Appreciate you waiting while I got my head screwed on right about this. When we look at this KSP, notice we're saying for every one of these that busts up, we produce 2 of those. So our mole ratio here is a 1 to 2 mole ratio. So if we say X of this busts up, it produces X of this and 2X of that. So if this equilibrium happens, lead chloride busts up into lead cation, one of these, since this is a molecular formula, 1 mole of lead chloride contains 1 mole of lead, but 2 moles of chloride anion. So if we say X of this busts up, it produces X of the lead cation and 2X the amount of the chloride anion. X is one of these, but for every one of these, we get 2 of our chlorides. So it's 2X. But notice that is 2X squared because we have the coefficient of 2 in front of it. So putting in those values for the X, we have X, concentration of lead, times the concentration of chloride anion, 2X. Since the coefficient in front of this is 2, it's squared. So we have equal to 0.4 times 10 to the minus 4th. This is 2x squared, which is 4x squared times x. That's 4x cubed is equal to 2.4 times 10 to the minus 4th. We're looking for the value of x. So to solve for x, we need to divide 2.4 times 10 to the minus 4th by 4. So x cubed is equal to 6 times 10 to the minus 5. We need to take the cube root of 6 times 10 to the minus 5. That cube root is 3.9 times 10 to the minus 2. So the molar solubility of lead chloride is 3.2 times 10 to the 3.9 times 10 to the minus 2 moles per liter. That's the chapter 16 quiz. If you have any questions, please make an appointment to come to my office so I can give you a better explanation of the problem, or if you have any other questions related to chapter 16, please make an appointment to come to my office during office hours. Have a good break.